BWIQ is B&W Tek's chemometric software designed for both on and offline quantitative and qualitative spectroscopy measurements. Today we are going to demonstrate how to build a classification model with Raman spectral data. In this video, we will import the spectra into the BWIQ software, define the class for each sample, classify the spectra using a principal component Analysis-Mahalanobis distance algorithm, and finally, use the model to classify new samples. In classification models, spectra of samples corresponding to specific groups are collected and then modeled according to their similarity to form a class. For this example, we will create a model using the Raman spectra of amino acids L-alanine, L-aspartic acid, and L-cysteine hydrochloride that were collected on B&W Tek's NanoRam handheld Raman system. 20 spectra were collected for each amino acid. To import the spectra into the BWIQ software, click File, Import, and select the file format you wish to use. Locate the dataset and import the files into BWIQ. The data files now appear in the Spectra window, along with the corresponding spectra. When developing classification models, we need to define the class for each spectrum in the software. Click the blue Addition button in the upper left corner of the Spectra window. A third column will appear. You can rename the column as Class by right-clicking the header and selecting Rename from the drop-down menu. Here, we will enter an integer value for each distinct class so that all aspartic acid spectra are designated Class 1, all alanine spectra are Class 2, and all cysteine hydrochloride spectra are Class 3. There are several ways to designate spectra files as calibration or validation samples in BWIQ. Spectra files can be manually designated as calibration, validation, or ignored files by clicking the drop-down button from the usage column. Files designated ignored will not be included in the final analysis. There are also several sampling algorithms available in the BWIQ software, which can be selected under Sampling. The parameters for the algorithm selected will appear in the Algorithm Properties panel. In the Algorithm Properties panel, you can change the ratio of calibration files to validation files, for instance, designating 60% of the files as calibration files and 40% as validation files. To apply the sampling algorithm to the data, click the blue Execute triangle in the Algorithm Properties window. The usage column in the Spectra window will show which spectra are designated as calibration samples and which are validation samples. For this type of qualitative analysis, we designate all files as calibration files. Next, we can add pre-processing steps to remove variation in the data set that is not related to chemical differences, but instead may result from scattering, instrumental variation, spectral noise, or background differences. The Raman data presented were collected using an automatic integration time feature, so the integration times for each spectrum are noticeably different. To normalize the data intensities, we will use a standard normal variate normalization algorithm. Click Preprocess, then Standard Normal Variate. The normalization now appears in the Algorithms window. When building classification models, an important step is to mean center the data, as we are interested in the difference of the data from a centered point, not how far the samples are from that center. Click Pre-Processing, then Center. The step is now added to the Algorithms window. Manual variable selection enables us to use the entire spectrum for analysis, or alternatively, to restrict the analysis to selected regions of the data. Using the whole spectrum for analysis will allow the model to be more sensitive to contaminants or changes in the samples that introduce signal in other spectral regions. However, it can be helpful to remove non-informative or noisy regions of the data from the analysis. For example, in this data we can see that above 1800 wave numbers, there is little Raman signal. Under Variable, choose Manual Selection. The manual variable selection is automatically added to the selected algorithms window. Now that we have finished adding pre-processing steps, we can add a classification algorithm. For this data, we will select a principal component Analysis-Mahalanobis distance classification method. Principal component analysis, or PCA, is an excellent exploratory chemometric tool that uses reduced variable space to define the greatest variance within a data set. With PCA, model scores and loadings are computed, and the 2D scores plot provides a visualization of natural groupings of samples based on the similarity of the data, with each sample represented by a single point in the new principal component space. To classify new samples with the model, we'll use principal component analysis in combination with a parameter known as the Mahalanobis distance, which measures the distance of a new sample to the center of each class. The Mahalanobis distance for each new sample is calculated for every specified class. The sample is classified by the software as the group that corresponds to the shortest calculated Mahalanobis distance. Choose Classification and then PCA MD. Click the blue Addition button in the Algorithm Properties window to add the PCA MD algorithm to the model. The algorithms that are listed in the Selected Algorithms window now make up the steps of our classification model. To save this training file with the extension .train, go to File, then Save As, and save the file. Training files can be edited and saved at any time in method development. To execute the model, click the blue triangle at the top of the window. This will perform the steps in sequence. Because our model includes a manual variable selection, the Manual Variables window appears upon execution of the model. In this window, we can type in the spectral regions of interest or use the cursor to define the analysis regions. Because there is no significant Raman signal above 1800 wave numbers for any of these amino acids in this data set, we will limit our analysis from 200 wave numbers to 1800 wave numbers in these spectra. The data shown have been pre-processed and are now mean-centered, with peaks in both directions around the 0 line. Upon execution of the method, a new model file is created. The model file is a .cmml file that can be saved and used to classify new samples online while connected to a B&W Tek Raman series instrument or offline using previously collected data. To view the scores plot, click the scores icon in the toolbar. The scores plot shows the clusters of the samples in principal component space. In this plot, we observe 3 distinct, well-separated clusters. These 3 clusters correspond to the 3 different classes of amino acids. Based on how close they fall to these 3 clusters, we can classify new spectra as belonging to one of these groups. There are several other plots available to view data, including loadings and variants. To classify unknown samples from previously acquired data, click Predict and load the prediction files in the correct format. The prediction results list the individual spectral file names along with the calculated Mahalanobis distances from each class in the model. The column to the right, labeled Class, shows the final classification for the sample, in this case either 1, 2, or 3. The class showing the lowest calculated Mahalanobis distance is the class chosen by the BWIQ software to represent that sample. Under Generate PDF Report, you can also save a PDF report which details the method parameters and the classification predictions. For more information on using the BWIQ software, please refer to the user manual as well as our other support videos. You can also reach us at www.bwtek.com/support. Thank you for watching.